Hi, I'm Everett. I'm a geochemist at Arizona State University, and I'm talking with you today about the composition of lithospheric fluids. I'd like to thank two of my recent PhD students, Tucker Ely and James Leong, for various contributions to this talk. The lithosphere is the rigid outer part of the Earth, composing both crust and upper mantle. The rigid properties of the lithosphere allow fracturing, which enhances permeability and makes lithospheric fluids quite common. There's an enormous range of temperatures, pressures, and compositions that represented by lithospheric fluids, and they circulate through both the oceanic and continental lithosphere. Geochemically, what's crucial about these fluids is they're responsible for weathering and alteration and the movement of material within the lithosphere. Importantly, the electrons are transferred from the lithosphere to its fluids because oxidation of iron and sulfur in the rocks occurs by water, which is then reduced to hydrogen. The hydrogen allows carbon dioxide reduction, abiotic organic synthesis, and the habitability of surface and subsurface environments. It also raises the possibility that the emergence of life is an internal process to the Earth. To give you a better idea of the lithosphere, here's a comparison of the compositional layers of the Earth, which are probably familiar: core, mantle, and crust, with continental crust being thicker than oceanic crust. And then the mechanical layers, where you see lithosphere on the outside. That's the rigid plates that move around on the asthenosphere in response to mantle convection. The lithospheric thicknesses are from like 10 to 200 kilometers. These diagrams emphasize the point that the lithosphere is composed of both crust and upper mantle. And the plot on the right shows that in subduction zones, it is oceanic crust and upper mantle material that makes up the subducted lithospheric plate. Now, subduction is a main way that continents are built, and so it's worth asking what the history of continental building is like. Well, as indicated by this figure, this is a topic of a lot of controversy. This shows a plot of the cumulative volume of continent as a function of time, starting 4.5 billion years ago and coming up to the present. And what's plotted in this figure are various proposed continental growth curves by various authors, as you can see. So there are some models that show the continents appearing very rapidly and early on into their full 100% of what we see today, and other models that show slow, gradual accumulation of continental material over the entirety of Earth history. There's less controversy about what the composition of the crust is. Composition is less controversial. Here's a pie diagram showing average crust of the Earth. You can see it's about half oxygen, and then the rest is made up of what are called the major rock-forming elements like silicon, aluminum, iron, calcium, sodium, potassium, magnesium. And then there's a tiny little wedge there for the rest of the periodic table. Here's another diagram showing different rock compositions, the mineralogy of those rocks. In the middle is a plot of silica content, and you can see that it's highest to the left and lowest to the right. And so let's start at the right, where the silica content is low. We have ultramafic rocks like peridotite, which is the crystalline form, an intrusive form, and its corresponding, maybe less familiar, komatiite, which would be a volcanic form. Komatiites are not very common on the Earth anymore, but were early in Earth history. These rocks, as you can see, are mainly composed of olivine and pyroxene with a little bit of feldspar. If we go to the left, to the mafic rocks, like gabbro and basalt, this is what the oceanic crust is composed of. And you can see that there's more feldspar, lots of pyroxene, and a little bit of olivine in these rocks in general. Moving to the left to intermediate and felsic rocks, these are the rocks that make up the continents, and you get familiar things like andesite, granite, rhyolite that are composed of feldspar, quartz, potassium feldspar, and the pyroxenes are replaced by minerals like amphibole and biotite. We see these changes in composition here in a series from basalt to rhyolite. You can see the amount of silica increasing, several other components of the rock decreasing in abundance, and the potassium and sodium increasing on the trend from basalt to rhyolite. Let's turn again to the ultramafic rocks at the right side of the diagram and consider what happens to them when they're exposed to water in near-surface environments. Here's an example of an altered peridotite from Oman. The dark material in the slide is the peridotite, which is upper mantle composition, and the light veins running through the rock are made of the mineral serpentine. So this is a process known as serpentinization, which not only transforms the rock composition and its mineralogy, but also dramatically transforms fluid compositions. Here's an example of spring water from a peridotite outcrop in Oman. You'll notice this water doesn't look very normal to us. It has a very high pH. It's a calcium hydroxide solution. When it encounters the atmosphere, it essentially inhales carbon dioxide, producing calcite, which is the white precipitate in the water, and is why the water looks so blue. Another feature of this water, as it emerges after reacting with the peridotite, is that it is extremely reduced, and in fact in many places is bubbling with hydrogen and methane, even though this water is not particularly hot or warm even. The hydrogen content of these fluids that have undergone low temperature serpentination is impressive, as shown here by the green symbols on the left on this plot of hydrogen versus temperature. The green symbols on the left coming from Oman, and they are the peridotite hosted samples. Notice that the amount of hydrogen in these fluids is greater than the amount of hydrogen in basaltic hosted hot springs in Iceland or the rhyolite hosted hot springs in Yellowstone. In fact, the hydrogen content of these serpentinized fluids rivals that of basalt-hosted hydrothermal fluids from the mid-ocean ridges, which make up the gray symbols on the right side of this figure. And those are surpassed only, as I mentioned before, it's the oxidation of things like iron and sulfur in rocks that leads to the production of hydrogen through the reduction of water. Here is a plot of the total reduced iron, or FeO content, of various kinds of rocks, plotted as a function of the total amount of magnesium in the rocks. And notice on the right we have the peridotites and the komatiites, and basalts on the left with the newly introduced set of type of rocks called picrites. So as the magnesium content of rocks decreases dramatically from peridotite to basalt, you'll notice that the iron content doesn't change that much. And so it's the oxidation of that iron in the primary minerals to the ferric iron in the secondary minerals leading to the hydrogen. So why is there such a wide difference in hydrogen in the fluids produced from alteration of these rocks? The answer lies in where the iron ends up. These are results of James Leong's calculations of what will happen during weathering of all these different rocks in terms of their potential for production of hydrogen. So this is low temperature weathering. Again, the rocks are arranged by their magnesium oxide content, and you'll notice that the potential for peridotite komatiite alteration to produce hydrogen is orders of magnitude greater than that from the alteration of basalt. And the reason is where the iron ends up. From peridotites and komatiites, the iron can fit into the mineral serpentine during serpentinization, and serpentine allows ferric iron into its structure. Serpentine is progressively replaced by chlorite and talc and in the other types of alteration, and those minerals do not hold ferric iron as well, and in fact the ferrous iron, the Fe+2, can move from the primary minerals to the secondary minerals with less oxidation going on. So this explains this offset and this potential of hydrogen production from peridotite and komatiite. If you're wondering why we care about the hydrogen production and the fact that it's greater from peridotites and komatiites, we can return to this plot of the growth of the continents and put the available information we have on komatiites, which are the eruptive version of peridotite composition rocks, on top of this. This is shown here as the komatiite volume, the percent of the continents, and you can see there's some variability in these estimates going back in time, and that they stop in the Archean when we start running out of the rock record. But if you examine that plot and imagine what's going on back into the earliest Archean and on into the Hadean, it's quite likely that komatiites made up a large percent of the continents and were capable of producing ample hydrogen from water reduction, which would be available then for abiotic organic synthesis. Let's move from the continents to the oceanic lithosphere and consider the circulation of fluids around mid-ocean ridges. This figure shows a schematic plot of heat flow as a function of the age of the seafloor from the youngest material forming at the mid-ocean ridges out to 65 million years. The smooth curve shows what would be predicted if heat flow was conductive through the oceanic crust. The dashed wobbly curve is what's actually observed, and the difference between those two curves is accounted for by hydrothermal circulation, which continues at lower and lower temperatures out across the seafloor to at least rocks that are 65 million years old. Observations like this lead to these sorts of schematic diagrams of fluid flow in this cross-sectional view, where we see cold fluids entering the crust, being heated at depth and reappearing as the black smokers along mid-ocean ridges. We've also learned that fluids circulate along the ridges, as demonstrated in this classic study. In the upper left is a map of part of the East Pacific Rise showing various locations of various hydrothermal systems and sample locations, as well as many, many earthquake locations. Those earthquakes are shown as a function of depth along the ridge in the plot on the right, and the authors interpret this fascinating pattern of earthquakes as representing how the fluid is moving through the system. So there's a downwelling of cold fluid, which triggers lots of small earthquakes, and that fluid circulates deep, causing a lot of seismic activity, and then moving back up toward the hydrothermal systems at the seafloor. There are, of course, big-time consequences for all this fluid movement through the crust and through the oceanic lithosphere. The composition of the fluid changes dramatically as it reemerges as screamingly hot water at the bottom of the ocean, and the rocks are also altered. Tucker Ely did an examination of the variation in this alteration by choosing from a database of more than 12,000 mid-ocean ridge basalt, or MORB, compositions. He did a selection of these compositions, and as you can see in this map, they are globally distributed. The compositions of these 1,884 mid-ocean ridge basalts are shown as probability density functions in the upper part of this plot. You can see that there's a lot of silica, as you would expect for basalt compositions, and then aluminum, calcium, iron, magnesium, all as oxide components, and on down into other ingredients. Notice that there's a distribution of all of these components, and that they tend to overlap, and it is this interplay among them that ultimately determines the alteration that can happen and has consequences for the composition of the fluid. Another thing that has a lot of influence over fluid compositions and rock alteration is the water-to-rock ratio, illustrated here schematically as a series of blue spheres showing the water and gray spheres showing the rock. And that's compared to the scale that we're using here for the logarithm of the water-rock ratio. So 0 would be 1, and you can see they match up there. -1, there'd be 10 times more rock than water. And then 1, 2, 3, so on. We see greater and greater water-to-rock ratios. The water-to-rock ratio is the x-axis on these figures, and the y-axis in these figures shows temperature going from about 5 degrees at the bottom of the ocean to 400 degrees in the high temperature hydrothermal fluids exiting hydrothermal systems. What's summarized in this figure are the results of about 16 million reaction path calculations that Tucker undertook in order to try to get an idea of what controls fluid and rock compositions in these systems. The plot on the left shows the average hydrogen concentration of fluids from all of those calculations, shown across temperature and water-to-rock ratios. The white curve in the figure shows this where seawater abundance of hydrogen falls, and you can see that most fluids involved in hydrothermal circulation on the seafloor are enriched in hydrogen compared to seawater. The plot on the right is complementary to the information on the left. It shows what's called the Shannon entropy, which reveals how the composition of the rocks matter in terms of the outcome of the hydrogen content. So there's a large area of that diagram that's labeled as low diversity. In that zone, it really doesn't matter what the rock compositions are. The amount of hydrogen is pretty much the same regardless of rock composition. And this might make sense because this is the high water-to-rock ratio zone of the diagram. Moving to the left, we can see that the Shannon entropy is increasing, meaning that there is a higher diversity, which means that the composition of rocks are having a greater influence. The variability in the rock composition is having a greater consequence on the variability of hydrogen that can be produced. So part of the diagram shows that you get similar results regardless of what your mid-ocean ridge basalt composition is, and the other part of the diagram is showing us that it's very important to know exactly what the composition of the rock is in order to understand its capacity for producing hydrogen. Here we are zooming in to this zone of high diversity in Shannon entropy. Here's a plot of the resulting hydrogen concentration as a function of temperature at a log water-to-rock ratio of -0.2 as indicated by the inset figure. Each curve represents a different mid-ocean ridge basalt composition, and you can see that they are spread out a little bit in this diagram. You can also see that at this water-to-rock ratio, which is fairly low, most of the calculated curves are high compared to the field measurements. However, as we move over in water-to-rock ratio, here the log water-to-rock ratio of 0, so that would be a 1-to-1 water-to-rock ratio, or a little bit higher values of water-to-rock ratio, here log value of 0.4 and 0.6, indicating that it is this sort of extent of water-to-rock reaction that is contributing to the hydrogen to hydrothermal fluids on the seafloor. Well, let's move back to the continents once again. Here's a diagram, a map, showing us not only the plate boundaries and the ridges, but the subduction zones and zones of great deformation in the continental crust, as well as many of the volcanoes that have been active in the last million years. And you can see that there's a lot going on in the continents. There's the mantle convection that is driving the plates around, drives deformation on the continents, and that deformation causes continental fluid circulation. Well, let's go to North America and one of our favorite volcanoes at Yellowstone. This map of the lower 48 shows the extent of ashfall from the last 3 big eruptions of the Yellowstone volcano. You can see that those are pretty large-scale eruptions capable of producing a lot of material. Yellowstone is still quite active and is well known, of course, for its hydrothermal activity. Here's a map of the outline of the park. Inside, the black dashed line shows the outline of the caldera of that large volcano, something like 50 kilometers across. And all the patches of green and black on this map show areas of hydrothermal activity reaching the surface. These are the various hot spring thermal areas that are so well known from Yellowstone. Now, the diversity of fluids in the Yellowstone hydrothermal system, and now thinking about fluids on the continents and the continental lithosphere, these compositions are dramatic, as illustrated in the next images. Here's a picture of a relatively high pH spring, probably around 8, that's at the boiling point. In these more alkaline springs, you can see that the fluid is quite clear. You can see way down into the hot spring. In contrast, here's a hot spring with a pH of around 2. As you can see evidence for sulfur in this spring. It's a little bit yellowish. It's also quite muddy. There's quite a lot of alteration of the rock going on, producing fine particles that produce this mud. And finally, here's an image of one of what we call the tomato soup springs in Yellowstone. So just given these images, you can tell that there's a wide variety of compositions of fluids in continental hydrothermal systems like we see in Yellowstone. This is demonstrated here in this figure showing pH versus temperature. All the symbols are values that we have collected over the last 20 years of fieldwork in Yellowstone. And then there's 2 boxes in this figure, one showing the temperature pH range of known bacteria, and the other the temperature pH range of known archaea. And I think it's impressive to think that just in Yellowstone we have so much variation in temperature, pH, and other compositional variables that the one location encompasses so much of the range of known bacterial and archaeal life. Well, I hope this survey has been useful for you in understanding what happens as fluids circulate through the lithosphere of the Earth, both on the continents and on the seafloor, and that the composition of those fluids depends on the reactions between water and rock, and that those results of those reactions are conducive to the support of life. Well, I'd like to summarize with some thoughts about water-rock reactions and the emergence of life. You've seen that there's deep fluid circulation. It's an inescapable feature of a geologically active planet like the Earth. The Earth offers enormous ranges of temperatures, pressures, and compositions in those fluids. And those compositions are capable of overcoming a fundamental challenge, which is the transition from inorganic to organic chemistry. The connection here is that water-rock reactions produce hydrogen. That hydrogen can lead to reduction of CO2 and abiotic organic synthesis. That can happen either in the ocean or continental lithospheric fluids. Also, at present, we know that these fluids produce conducive climate conditions that persist for long durations that support microbial life on the planet. And this raises a question of whether the emergence of life is an internal process on the Earth, driven by these kinds of water-rock reactions that happen as fluids circulate.